The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, I hope you had a wonderful Valentine's Day. I share you a story. I always make those reservations and put something on my calendar. So I put on calendar my last slide. I give a public lecture at Boston University. It turns out my sponsor and myself, none of us noticed what's date last slide. So you can imagine how many people showed up on this public lecture. There was one interesting, in fact, interesting couple. And they were sitting in my lecture. And I was talking about the thermoelectrics. And after that, I had a chat with them. And his wife actually said, "Oh, today is his birthday too." So, birthday and Valentine's Day. And so I was very pleased. Okay. So coming back, last time we were talking about a very raw picture of the microscopic energy carriers. We say, okay, if we look at the molecule, what are the energy, how much energy they have, what are the forms of energy, and then we see how many we have. Particularly, we introduced the Boltzmann factor, the statistics, and say what's the average energy? It's a KT, right? So the taken translation as one example. And if you think about the KT, if it's a molecule, you can use the mass 1/2 mv squared equals KT, and you can actually say the molecular speed is very high. The molecules are moving a few hundred meters per second, except they are doing random motion. And then we see how far they travel. That's the mean free path. Right, we estimate the air molecule, the mean free path is about 100 nanometer. And with that, we give a very simple derivation, kinetic picture of the transport, the Fourier law of heat conduction. And at the end, we went into the size effects. So if you transport the characteristic length is less than the mean free path or less than the wavelength of the mature wave, you will get, say, either classical size effect or quantum size effect. And now that I went through the quantum size effect very hand-wavingly, and also that's the end of lecture, so hopefully today we can make that up. And in today's lecture, I'll be talking about materials waves and energy quantization, and this is chapter 2. So today and next Monday, use 2 lectures, and we'll go through quantum mechanics. Okay, so that's the ambition there. So what I want you to get is some basic ideas of appreciation for the importance of energy quantization. And say you see with this very simple view, you can actually understand a lot of things. So let's start with the wave. I said in the last lecture, when you have an interface, always because the interface thickness is characteristic length is 0, so it's always good to say what are the waves. You have reflection of the waves. So let's start with a general wave, right? You all have learned about waves in one form or another. What are the most important characteristics of waves? Right? What are the basic characteristics of waves? you have phase, right? But say, going even more basic. Amplitude, wavelength, frequency, right? So basic characteristics of waves. And then when we think about the frequency, we're thinking about time domain. And then when we think about the wavelength, we're thinking about space domain, right? So if we say I have a wave, simple wave, a sine wave, right? Here is the period. And in the case of time domain, this period is time. In the case of space domain, this is the wavelength, right? So time period or wavelength. And but we normally do not like to write time period. We like to talk about frequency, right? So can anyone tell me what's the relation between frequency and time period? Mathematics now. It's a Fourier transform, right? So if you have periodic function, you do your Fourier transform, the inverse is 2 pi over that period. So we have period and frequency. This is the Fourier pair, right? We of course frequency is 2 pi over the period. So at least in time domain, you're very comfortable with frequency, right? And in space domain, we have wavelength. What's the corresponding Fourier inverse? I'm sorry?
Wave number.
Wave number. That's probably a less familiar. You don't use it often, right? So the wave number eta equals 2 pi over lambda. It's a Fourier pair, right? And of course, when we talk about frequency, there's another frequency we often use, angular frequency, right? So omega is the angular frequency is 2 pi nu, and correspondingly, I have a k equals 2 pi eta, or is 2 pi over lambda. Okay, this is a free space.
Nu should be 1 over here.
Yeah. Nu is a frequency.
Nu, you were, I'm sorry, okay, yes, sorry. No, all this has a problem. 1 over t, and otherwise I might have 2 pi there. Thank you. Okay. But space is more complicated than time, right? Space has direction. So when a wave traveling in a certain direction, I can say this is the wavelength in that specific direction. I can have kx, ky, kz. So the here k in general is a wave vector. So it's a kx, ky, kz. And so we have wave vector. I want to be consistent in using capital. So this k is the magnitude of the wave vector, right? So now we have the space, we have the time, basic characteristics that characterize a wave. It's periodicity. And now we can write the simplest wave, simple form of a wave, right? The simplest wave is a sine wave or cosine wave, constant amplitude, right? So let's write a simple way. And I'll write using a general symbol phi, and this could be a vector. It could be a vector wave. Think about acoustic wave is a vector wave. Electromagnetic wave is a vector wave, right? So a vector that has an amplitude, and I write a constant amplitude, and I have a time omega t minus k times x. You can go to say substitute omega equal to 2 pi nu, k is 2 pi over lambda. So this is a wave traveling in the x direction. And then I have a unit vector represent this vector. When I say the direction, that's the wave traveling direction. So I have two directions there. One is the wave traveling direction. The other is the wave oscillation direction, right? If you think about an electromagnetic field, the wave is traveling forward. And we know electromagnetic field is a transverse wave. So electric field is perpendicular to the wave traveling direction. If you think about the acoustic wave, the sound wave is a longitudinal wave. So the wave vector is propagating to you, and the oscillation, the pressure wave is also in the same direction, longitudinal wave, right? So I have two directions, and this is I associate as polarization of the wave. And this x is the direction, the wave propagation direction. And this is the field. Y is the field direction. Right? So this is the simple wave. Of course, A here is the amplitude. And somebody mentioned the phase. So phase of the wave is what's inside. So omega t minus kx. That's the phase. And for a constant phase, so a plane of a certain phase value, and if this is a constant, that's a constant phase plane. And you can see this plane is moving at dx dt equals omega over k from here. Take a derivative. Right? So that's the velocity of the constant phase. So this is called the phase velocity. And of course, the most common relation you're probably familiar is the light, where you have for light in vacuum, we know frequency times wavelength is the speed of light. I use a small c, or here let's put a constant. And so speed of light, and this we say omega equals ck. Right? For light, it's a linear relation between omega and k in free space. But more generally, as you will see very soon, there is a very complex relation between omega and k in general. So omega and k in general case could be a very complicated function of the wave vector. And what that means is in different direction, right, the wavelengths and frequency have very complex relations. And this is particularly true when we go to solids, photons, and electrons. So that's just a wording down the street. And so here we talked about phase. We talked about sine wave here. But in mathematical operation, if you take a derivative of sine, what do you get? Cosine, right? And that's not convenient. even though it's simple enough. A simpler derivative where it goes to itself is the exponential function, right? So very often, rather than representing a wave in sine and cosine, I'm going to represent it in exponential functions. So this is a complex representation. That's really for mathematical convenience. And if I use a complex representation, I will write this wave as I can combine A and Y into a vector. That's the wave oscillation direction. And then I will write exponential minus I omega t. So I use a complex omega t minus k times x. Let's first do 1D. Okay. So if you see this, right, of course, it's easier to take a derivative of an exponential function. And what I have here really means I can write this exponential back into cosine and sine. So I have cosine omega t minus k x minus I sine omega t minus k x. Right? So I have a real part and an imaginary part. And in real life, of course, the waves normally is either sine and cosine. So the case, you stick to say, OK, if my solution, if my initial condition, my boundary condition, all is for the real part, cosine, then at the end, after I solve my problem in this complex representation, my real part solution is what I'm looking for. If you stick to the imaginary part, again, you have to look at your initial, your boundary condition. And as long as you meet the sign, those constraints, you see the imaginary part is your solution. So that's this complex representation gives you mathematical convenience. Another comment is, if you look at there, I put a minus sign in the front, right? That's just my preference. It turns out that even different book, people sometimes use positive, some use negative. And particularly when you go to read optics, and some books use positive, some people use negative. And that creates a lot of confusion because that will mean later on you will see there's an optical constant that has a real part, an imaginary part, and in the front it could be a positive and negative sign. So unfortunately, that's the case, and that's we don't have a solution there. Okay, and the other comment I want to say: these waves are traveling waves, right? Last lecture I mentioned a standing wave. If you play guitar, you clamp the two ends. That's a standing wave. And here is a wave that's traveling, in this case, omega t minus kx into the positive x direction. If it's a plus kx, that's a wave traveling into the negative direction, x direction. Right? More generalization. Here is a wave in the x direction, but I said k is generally a vector. So if I write a three-dimensional plane wave, and the general form for this wave is A, that's again the polarization direction, and amplitude exponential minus I omega t minus k is a vector dot r. So this is a plane wave in complex representation in 3D. Okay, general space. And we mentioned here is a traveling wave. and I can use traveling wave to construct the standing waves. Example, let's talk about, think about standing wave. So I have two opposing traveling waves, same amplitude. One is sine omega t minus kx. So this is a wave traveling from to the positive x direction. I have an opposing wave traveling in the negative direction, same plus kx. Right? So two traveling waves now. And I superimpose them together, what I get. Right? Add two sine. It's two sines. Sine, cosine, right? So the negative part cancel. So I will get a 2a sine omega t cosine kx. Right? So now you can say I have standing wave, because these are my loads. When the kx equals 0, it doesn't depend on time. So my 0 point is fixed. Right? You play your guitar, you press your finger, and then you fix your notes there. Okay, so I can use the standing wave to construct the traveling wave construct standing wave. Last comment on wave. What's the energy of the wave typically?
A square.
So energy of wave is typically proportional to the square, right? The square. So the energy is typically proportional to the square of the wave. Right? The amplitude is higher, larger energy. Those are the basic characteristics. Right? So with this, let's go to talk about material wave. And that's we have to go into the quantum mechanics. And let's talk about how it started. So this is a very interesting history in science. If you look at this is starting about with the optics, right? And you heard probably Newton optics. And of course, when Newton did the optics, he treated light as particles. He didn't think light was a wave. And so it took a lot of time to challenge Newton. And there are Huygens, there are a lot of people. Eventually, it was established light is a wave, is not a particle. And the final triumph is Maxwell equations for light, right? So going from particle to wave, and Maxwell equations solidify the wave nature of light. And that seems to be all settled problem, except, let's say, if you go to look at the history of physics, and there are two problems that people wrestle with. One is black body radiation. And it was found through experiment that this is a wavelength, and this is the emission from black body at different wavelengths. And this is a typical curve of black body radiation. And with the classical the classical mechanics of black body for light, unfortunately, the trend should be always like this, right? So that was a big puzzle for physicists at the time. And the other is all related to photon is the hydrogen absorption spectrum. And it was observed that the absorption happens at discrete lines. And the continuum mechanics say you should have a continuum spectrum, but say the measurement actually say that's not the case. So to answer this puzzle, a lot of people tried. And it was Planck that first introduced a radical concept. Right? And he's rather than, when we talk about electromagnetic wave, right, we say the energy is proportional to amplitude squared. Okay, it's a continuum. You can have any amplitude, right? So what Planck introduced is that you cannot have any continuous function of that, say, amplitude. So your energy is not a continuous function, and the energy at specific frequency can only be multiple of this h nu. And this h is the Planck constant, is 6.6 10 to the minus 34 joule second. Right? N is an integer. N is 0, 1, 2. So the energy of the light cannot be any value. It has to be multiple of this h nu. So that was a radical concept, discretization of energy. And so what happened was Einstein was, you know, he was a patent clerk. He read Planck's theory, black body. And he did another radical proposal. And he said, this means that the electromagnetic wave is granular. It has particle characteristics. So it came back to a particle. A particle has energy and momentum. So what's the momentum of light? Right? So you all know Einstein has his famous energy relation, mc squared. Right? And a momentum, P, is mass, because light is not a particle that has mass, right? So we need to get rid of the mass. And so it's mc. So we have mc is mc squared divided by c. That's the energy. Energy is h nu divided by c. So it's h over lambda. So Einstein argued that the momentum of this light quanta is h over lambda. And now the light has both, say this basic quanta has both energy unit h nu and the momentum unit of h over lambda. Right? So with that, he argued that light say has a particle. This is a granular wave. It has both a wave and a particle, right? And in fact, if you go to read Einstein paper in 1905, he published 4 papers. And one is on relativity. The other was on Brownian motion. Brownian motion was his PhD thesis. Okay, And at the time, he didn't know Brownian motion. He didn't know there was a Brownian observation. He was just trying to infer the size of atoms, molecules. And then he hypothesized this energy quanta. And I wasn't sure the other one was about the, this is the photoelectric effect, but I thought this one is together with the photoelectric effect. Okay, anybody remember? 4 papers, like only. So if the photoelectric effect with this together is the one, then I can only count 3. Maybe you go back to check. So with this energy quanta concept, he explained another experimental observation. That's the photoelectric effect. And the photoelectric effect is when you have 2 electrodes, metal electrode, you shine light onto it, you will have a current flow. Okay. And the physics is that the light get the drive electron out of the metal, so go from one electrode to the other electrode. Okay. But the puzzle was that the current should be proportional to the intensity of light. So the more light they come, the higher current you have. But the experimental observation is if the light wavelength, or say frequency, right? Wavelength is too long or frequency is too low, it doesn't have current. So there's a threshold for this photoelectric effect. And Einstein's explanation is this is where electron sits, right? Later on, we'll say this is the Fermi level. And here is it needs to come out of the metal to the vacuum, right? And there you got a difference in energy. And this difference here is vacuum, is the work function. So that's why you say you have to have this energy quanta h nu larger than the work function, and it's like you get one ball, you lock out another ball, right? So this is the consequence of this granular picture of light. And in fact, if you go to check the Einstein papers, so sometimes I joke, he's a heat transfer guy. If you go to check Einstein papers, all those arguments were based on thermodynamics. Right? If you think about the time, there was no quantum mechanics, and they only had the classical mechanics and the Boltzmann, at the best, the Boltzmann statistical physics. That was the foundation at the time, and Maxwell equations, right? So very interesting to read those articles. And it took actually on this quanta of light, it took Einstein another 10 years or so to think more and came up with the idea of stimulated emission. Right? That's also further say the light characteristics. Okay. So with that, we have basic relation, Planck-Einstein relation. The energy of the quanta is h nu, and the momentum of the quanta is h over lambda. And this is for EM wave. And later on, at the time, they didn't give the name photon. So it was until 1930s, somebody suggested this basic energy quanta for light is called photon. Okay? And so that's where Einstein stopped on this photon. And I said he said stimulated emission, all that. And then there was a graduate student. His name was de Broglie, doing his PhD thesis. And he looked at this Planck-Einstein relation for the quanta, and there is going from a wave to particle, right? And he made a very bold extrapolation. He said, why just for the electromagnetic wave? Why is not for any particle also has the reverse wave characteristics? So this de Broglie further extended this to matter waves. He didn't have any equation. He couldn't write and say a wave equation. But say I have to admit I didn't go to read his thesis, but I heard that the thesis was very short, and just to say reverse, and made an argument, and then people went to do experiment, and the experiment on that was by Davidson and Gemmer. So, okay. So, if we think about the material wave, right? Let's take, say, the wavelength of a matter is h over p. And I can go to calculate what's the wavelength. And I take any object, 1 kilogram, and move 1 meter per second. What's the wavelength? That's just h, right? P is mv, is 1, and wavelength is 10 to the minus 34. So I think this is probably related to gravitational wave. People are still trying to establish a relation between gravitational waves and the quantum mechanics, all those. But that's too short. So your m is too large. And but see, if you go to take an electron mass is 10 to the minus 31, 9.1, 10 to the minus 31. If an electron moves 1 meter per second, the wavelength is very long because the 10 to the minus 34 divided 10 to the minus 31 give you 10 to the minus 3 meter. That's a very long wavelength, right? In fact, it's too long. So the Davidson and Germer experiment was actually shooting electron, yes?
Your velocity is always relative?
Well, say you should go to, ideally you should go to relativistic velocities when you go actually electron. When you say relative, what do you mean? Relative to each other or relative?
For the first example, when we said 1 kilogram and 1 meter per second.
Right.
1 meter per second is always relative. So
relative to which observation system, what do you mean?
Yeah.
I don't know. Good question.
Okay.
Okay. So relative to the emitter of the electron, relative to the question is relative to what was the observer. I think it has to be relative to observer.
So the wavelength is always dependent on where you're observed.
Yeah, should be right. Let me say if you think about Doppler effect, right? A moving object emit and you have different wavelengths depends on the speed. Okay, so lambda equals say h over p, and what they did is shoot the electron on aluminum foil. So aluminum foil has atoms, right? And when it's periodic arrangement of atoms. So when you have a wave comes in, and a wave see periodic structure, you have constructive, destructive interference, you have diffraction. So they only go to certain directions. So what they observe is they transmit it, if you look at the different directions, and transmitted electron has spikes as an angular. Right? And that established the evidence that electrons waves. Okay, so all those people got Nobel Prize, of course. And so that's the this in fact is the foundation for the tools you'll be using. Some of you use it in research. The typical transmission electron microscope, TEM. Microscope, right? So how it works? One way is you use a very sharp tip, tungsten tip. You have apply a voltage between this tip, a high voltage. You drive the electron out. Okay, so this is a field emission. When your voltage apply high enough or tip, the electron get enough energy, they go overcome they jump to the vacuum. Okay, this is field emission. You can also heat this tip. That's a thermal emission. Get the electron out of the tip. And then you apply another high voltage to accelerate this electron. And typical, say, TEM, people say how good is a TEM. It typically means how short is the electron wavelength. So you actually want to accelerate electron to very high velocity. And typical TEM voltage is about 100 keV. 100 keV, so kilovolt. So that's the voltage applied to the electrons. And then say you got the electron focusing optics. So it's electron optics, not the normal optics. And then focus the electron beam to a very small spot. And you look at because the wavelength depends on the momentum, right? So the higher voltage, the shorter wavelength, so you can look at smaller structures. And you can do transmission mode, look at the reciprocal space. This is the diffraction pattern, or you can look at the real space. So this is a TEM. And the other is SEM, scanning electron microscope, right? And it's similar in terms of driving electron out. And what it does is, say, it looks at the reflection. So in this case, TEM is transmission. So you have to thin your sample very thin. And that thickness is typically 2,000 angstrom or so, so that the electron can go through the sample. You look at the other side, right? So that's transmission. And say SEM is your electron comes in, and you look at the reflected electrons, scanning electrons. So you scan your the electron beam on the surface. And in that case, you don't actually accelerate the electron to 100. Typical SEM voltage is about 20K. Okay? And 20K is still pretty high. And the resolution is not as good as TEM because of the voltage. Right? So this is in terms of what led to the wave-particle duality. And at the time, there are a lot of young people, right? If you look at Heisenberg, Dirac, I remember, say they were all in the 20s, and took this idea and developing the quantum, say the description for the quantum mechanics. And so we have Schrodinger. Schrodinger is an older guy, but he's younger than me. He was in the 30, 35, or 38 range. Okay, Schrodinger equation. So it turns out, before Schrodinger, Heisenberg developed matrix description for the wave description of the matrix-based quantum mechanics, right? And the story was that in one summer school, Schrodinger was in a summer school and learned about the Broglie idea of material wave, and somebody said there should be a wave equation there for this material wave. So Schrodinger wrote the equation, the wave equation for the material wave. And this is the h bar squared 2m, and that Laplace operator. And this is the wave function, and plus potential times the wave function equals I h bar, the time derivative of this wave function. Okay, so that's the Schrodinger equation. And Schrodinger himself didn't know what this phi really meant, right? And if you look at it, take a U. This is U is the potential. So if you have an electron, you have a particle, what's the potential constraint? Right. And then let's say if we take out this U, you think this as a temperature, that looks like a heat conduction equation, right? The first order time derivative, second order space derivative, and heat conduction is not a wave equation. So the magic came from that I, right? This I is negative square root, right? That's the imaginary number there. If you think about any other equation that has I, is there any other equation in physics that has I?
Euler equation.
Huh? Euler equation. Where is the I?
E to the I plus 1
Okay. So this is really what it has is cosine t, say the wave function is a function of space and time. And at the time, Schrodinger didn't have a right interpretation, and it was born and gave the right interpretation. But this caused a lot of trouble, because they born say this wave function itself is not an observable quantity, and it's the psi times the complex conjugate, because normally if you solve this, you'll get an imaginary number there. What does the imaginary number mean? So it's a complex conjugate will give you a real number. And of course, this will be a number that depends on time and space, right? And the interpretation is this is the probability. And this is the probability density function of finding this particle at the space r and time t. Okay, this interpretation caused a lot of trouble, because that means everything is uncertain. It's a probability, you have uncertainty. And Einstein didn't like it. Einstein never agreed with quantum mechanics. And Schrodinger himself didn't like it. He even regret he wrote this equation. That's what I heard. Okay. But say this was really the foundation that we use now for a lot of things. So if you read the fight and the debate, although say it was Planck who discovered Einstein, Because if you see, at the time, Planck was a very big shot. In Germany, there's a Max Planck Institute. That's Planck. And he was very established, and Einstein was a patent clerk. And Planck was the editor for this Anna of physics, the physics. And so when Einstein sent paper, he actually published his paper, even though Planck himself he didn't quite understand his paper. This relativity, right? Nobody claimed they understand it. And but say later on, I say this fight between Einstein and the quantum mechanics people got very, very hot. And so let me just make the clarification. This is Laplace operator, right? So is whatever, if in the Cartesian coordinate, is whatever behind, you do the, this is Laplace. And now since cosine here is a probability density of finding this particle in, say, location and time, so you have a normalization. And in probability, at the end, finding the particle in the space you consider is 1, right? So the normalization for this probability is the wave function integrated over the time of the space of the whole domain that you consider should be 1. And because it's a probability, so there is the expectation value, right? And it turns out in quantum mechanics, everything is uncertain. The space, the momentum, the energy, the time, everything. And then you have to calculate what's the most probable value and then what's the uncertainty with that associated with this expectation. So we have this expectant value. And for any quantity, this could be, so we use, this one is now a number, expectant value of any quantity is integrated over, again, the same volume. And the wave function. And for that quantity, normal representation is an operator. So this quantity in quantum mechanics is an operator. And so we have the operator operates, say the complex conjugate of wave function operator operates on the wave function and times the complex conjugate. So operator operates on the function following it. What does it mean? So let's write the operator for a few common quantities. For position, it's easy. That's just a normal R, right? And but for momentum, this operator now is a derivative. See, a momentum operator is mass I h bar gradient, right? So this is the gradient operator is d dx in Cartesian coordinate I and d dy j and d dz k, right? So now if you put it here, this wave function goes here, so it's d psi dx, d psi dy. That's the operator. You take that derivative, and then you do the complex conjugate, you integrate, and that's your expectation value. Okay? And for energy, that operator is Hamiltonian, and you can actually think about the momentum. So it's the kinetic energy divided plus the potential energy. So it's 2m, that's a kinetic energy plus the potential energy. And now the P is an operator. So if you do your, say, IH square, and this Laplace dot product give you, or gradient operator dot product give you Laplace. So what you have here is a minus h bar square 2m Laplace plus the potential. Potential is a function. It's another gradient. So you can just, it's the product. So you can go back to look at the Schrodinger equation here, right? This is the kinetic energy, potential energy. And that's what we have there. OK. Now, let's look at first think about the general solution for the Schrodinger equation. I want to get the time-dependent term out first. So for that, I will assume the energy, the potential energy is a function of space only. It's not a function of time. This is not always the case. For example, when I want to solve a problem, light interact with electron, right? And in that case, I have a time-dependent potential, because light interact, the interaction will be time-dependent. So, but for the moment, I want to find the only given potential, what's the energy of the system. So I say a space-dependent but time-independent potential. And in that case, if you go look at your Schrodinger equation, you see here, right? This is time-dependent. This one is space. This one is space. So I can use the separation of variable to separate the time and space part. So I'm going to write, in this case, I'm going to say time, space, into a separation of variable, space, and time function. OK? And then we substitute into the equation. So let's, if you substitute into this equation, what you find is I have psi h squared 2m, the Laplace operator psi plus u psi equals I h bar y dy dt. So this is the same as we solve any separation of variable problem. This is space dependent only. This is time dependent only. So the only way they equal to each other is each of them is a constant of that separation of variable. So let me denote that constant as E. It's not an incident I use E, because this E, it turns out, is the energy. OK. So this part is easy to solve. It's the first order differential equation. When I solve it, what I have is y is a function of time, is exponential. OK, so say a constant times the exponential minus I e over h times t, right? So e over h, I just use another notation, omega. If you think this E is energy, but let me move. So it's minus I omega t. So that's the time-dependent term. Okay? And the space-dependent term, once I have the separation of variable, the space-dependent term now is, you see here is I multiply this E times psi. So what I have is the plus U minus E psi equals 0. So this is a time-independent Schrodinger equation. And this is the one that you use when you want to solve, say, most problem. What's the energy of matter? What's the energy of an electron? What's the energy of, say, crystal? What are the allowable energy of atoms, vibration, and crystal? This is the Schrodinger equation, time-independent Schrodinger equation. And the difference of this is, if you look at it, what's different for each problem is really this U. It's a potential that this matter wave, electrons, atoms, right? What's the constraint? They're constrained by different potentials. And this different potential give you different energy state of the matter. Okay. And a few more comments on the Schrodinger equation. And I said this is a separation of variable here. This is E. And in fact, you can go to show, because we say the energy operator, where is my energy operator here? Here, energy operator is H. So it turns out that the H, if you substitute using what's the expectation value and go to use the Schrodinger equation, you'll find out that this H expectation value is actually E. I'm not going to go through all the math, but so that separation of variable constant E represent actually the energy of the system, the allowable quantum energy, quantum states. And the other comment is, this equation, you actually use the equation to solve E, right? So this is different than you solve a heat conduction equation where you give boundary condition, you find the temperature distribution. It's an eigenvalue problem. This E is what you want to find. Given boundary condition, given potential, you typically have an eigenvalue, allowable value for that E. That's the quantum constraint give you, say, not all the energy of the system, say any energy, but let's say the allowable value. A few more comments. And because the wave function is probability, right? So we have basic relation one is Heisenberg. Uncertainty principle. You all have heard this. So any value has its spread, right? Expectation and the standard deviation. So if we define the standard deviation, delta Q equals, and the typical we define the standard deviation is this Q, that's the operator, remember, minus the expectation value square and the expectation value, right? That's how we define standard deviation. Okay, this is the operator. This is expectant value. So operator matter expectant value. And again, you operate on, you put in this into your expression omega. That's how you calculate the standard deviation. And what the Heisenberg uncertainty principle tells you is, for example, momentum, this copper pair, momentum and space are the two conjugate, and you can never reach a precision that better than h bar over 2. H bar itself is h over 2 pi. And the same for energy and time, you can never do better than h bar over 2. So this is the Heisenberg uncertainty. And finally, after this, we'll go to solve more Schrodinger equations. Okay. My final comment is, again, from Schrodinger equation, we're not proving, you can manipulate the Schrodinger equation, and the way you do it is, for example, here is real. You multiply complex conjugate on both sides. And the second time, you take a complex conjugate and multiply by real. And then you take the difference of the two. And what you get here is like a continuity equation. So what you have, in that case, I will get the square. So that's the probability density, right? Time derivative of that probability density times a flux term, the divergence of the flux equals 0. So this is like a mass continuity. And this J is your mass flux. So the particle flux for in the quantum term. So this is flux is I h bar 2m complex, say the wave function, and we need this expression later on when we look at what's the electron reflection at the interface, right? If you do charge transfer, you need to look at how the interface will scatter or reflect the electrons, and that's a material wave. And we'll also do what's the electromagnetic wave reflection at the interface. And in fact, later on, we'll be starting with two different equations, Maxwell equation for electromagnetic wave, and the electron equation from the Schrodinger equation. And you'll find for all those waves, the final expression of reflectance is very similar. OK? So any questions here? Let me recap. It's a lot of material. That's a basic, lot of things. So what we have for a material wave, and it's covalent. At least let's say I like to use Schrodinger equation. Physicists actually like to. They're different. There's 3 different ways to do quantum mechanics. You can go Heisenberg that can do matrix representation. And then you can go Dirac, and this Dirac do operator, quantum mechanics. And then a lot of physics books is written in operator format. Okay, and you go to read papers, most of the time they're actually written in operator format. I'm not familiar with that. Schrodinger equation is the master equation here, and the wave function, right? So it's like kinetic energy, potential energy, and time-dependent term, right? And this sign is the wave function. It doesn't have meaning itself. It's only through the the wave function multiply the complex conjugate that gives you the probability of finding this matter a certain space R and time. And this, because of that, everything in the quantum world is probability based. So you have best say the expectant value. You have standard deviation, right? So you have the uncertainties, and that's the basic idea we have. See what we introduced today. And what I want to do next, I promise you, right, is say every week I want to go to look at some journals. And then we looked at last Wednesday, and this is Wednesday. So what journal you want to look? You can ask me questions while I turn on the projector. I like that idea. So it turns out the simplest solution of the Schrodinger equation in the past was pretty much an academic exercise. I mean, say every book will take that as your first solution of Schrodinger equation because that's the simplest mathematics. That it was the problem I talked in the last lecture. There's a film with standing wave inside. That's 1D, right? A film, so you have boundary condition, and the energy solution. What's the energy quantization? We'll go through that mathematics in the next lecture. But you have seen in the last lecture, let's see, that's the simplest solution, the energy quantization. So in the past, this was really considered just an academic exercise. But that changed in the 1970s. And that's because people start, well, of course, people have looked at thin film deposition for 100 years, right? But in 1970, there was this idea of if you deposit perfect film, you actually can make quantum wells. You can see the energy quantization. And this was by Isake and Ray too. And they actually made the superlattices, a multi-layer of thin films. So it was suggested to look at applied physics letters. I didn't coordinate with him, so that was a suggestion. Okay, and this is applied physics letters. Let's see, research highlight. Let's look at a few research highlights. I did actually look at this morning, so what I found is let's go to the last two of this research highlight. Right? So I say here you have two. One is reduce, improve photo response, indium arsenide, gallium arsenide, quantum dot infrared detectors. Now you can see the quantum dot, the energy quantization, right? And the next one is the effect of electron blocking layer on the piezoelectric field in indium gallium nitride, multiple quantum wire. So this energy quantization is widely explored, particularly in photonics field, to make better lasers, better detectors, and so let's go a little bit deeper. No, this is not the paper. It's actually the paper beneath it. That's the one I should click. Okay, this is the quantum dot, right? So what you will see, the energy band diagram that's drawn. So It's a thin films, layers, right? And it turns out this quantum dot, indium arsenide quantum dot, is when they grow those films. So it's through those molecular MB, molecular beam epitaxy. And you have a heated cell. You do ultra high vacuum. You don't want any junk there. And this molecule, say the atom will evaporated and goes to a target at a control rate. And when you grow this indium arsenide film, it has it's a crystal. Normally you should do a film, but because the lattice constant is very different, so they are strained. Okay, so once you grow to a certain thickness, they cannot grow a film anymore. The stress will break them up into dots. Okay, so that's how people make those control the quantum dot. And then when they are very small, feel you see here how much 2.2 molar layer. ML is a modern atomic layer. Okay, and in that case, the dots may be just a few nanometers. And you have energy quantization. And these are some examples of an energy band diagram. We'll learn more in this in solid. But essentially, you see this is the energy diagram. Let's say last time I say a particle in, a standing wave, right? So this is the film, the standing wave, and those are different energy levels. If it's a half wavelength or full wavelengths, there are different energy associated. And with that, you can be responsive to different wavelengths of light. Okay? So this is this is the one example. And in fact, a lot of those very simple cases you learn in classroom these days is being used, of course, with complication of real materials and not the ideal solution that you say I gave them on board, but say the basic ideas are there. And that's what I'm hoping you take those and you can, don't get afraid, you can start reading some of this paper and get familiar with what, not only what you're doing, but what the others are doing. Any questions? Let me just go to the next one. Make a few comments. The next one is gallium nitride. Okay. What's so special with gallium nitride? It's a wide band gap. And in the past, so gallium arsenide, the previous one is a longer wavelength. So the laser, semiconductor laser, first you have red gallium arsenide based, and people want to have green and blue. Okay, and a lot of people spend a lot of time trying to develop blue lasers. And the first they look at zinc selenide. And so you look at the band gap. We'll talk about band gap later on. Okay, but nobody can make them very successfully. So there was a guy in Japan. His name is Nakamura, and he was not a PhD. He was in this company called, I think it's Nichia. And they supported him for a long time. He had a master's degree. He was playing with gallium nitride. And he was able to make the lasers and say the emitting light at the blue. Everybody was shocked because nobody was working on gallium nitride. People were looking at the zinc selenide, their direct, because it's hard to grow those. So gallium nitride, that was in the 90s. And since that, people are making optic device, making electronic device. And again, if you grow very thin films, you can have that energy quantization, the quantum wells, right? In the case of particle is a dot, is a quantum dot. A film is a well. It's actually a 1D problem, 3D problem. Okay? So wait for next lecture. We'll solve the 1D problem. Okay, I'll stop here.